In order for the architecture profession to maintain its leadership position in the creation of the built environment, it is imperative that architects take a leading role in the adoption and integration of advanced materials and techniques into the construction community. The subject of this presentation is the use of fiber-reinforced plastic, or FRP, commonly known as fiberglass, in architecture and civil engineering. By the end of this presentation, the viewer should understand and be familiar with composites terminology, the history of FRP composites development, the two types of plastic polymers, polymer composites and their advantages, fiber-reinforced plastics and how they are made, physical properties of FRP composites, sustainability of FRP composites, some significant projects designed in FRP, and additional composites information sources. Plastics terminology. The terms plastic and polymer are used interchangeably throughout this presentation. FRP means fiber-reinforced plastic. GFRP means glass fiber-reinforced plastic, or fiberglass. CFRP means carbon fiber-reinforced plastic. And PFRP means pultruded fiber-reinforced plastic, or pultrusions. There are numerous uses of plastics in construction, from paints, coatings, sealants, carpeting, wall covering, laminates, counter surfaces, piping, doors, and windows. This presentation will concentrate on the use of FRP composites in architecture as structural components and as exterior cladding. A quick history of plastics. Plastics are natural or synthetic polymers that can be molded into permanent shapes. They are today's most widely used materials, and they can be found in every facet of modern life. Knowledge of the history and development of plastics is important in order to understand this industry, especially those developments of particular interest to architects. Let's take a look at the plastics timeline, courtesy of the British Plastics Federation. The plastics industry is over 800 years old. The first known use of plastics is in 1284 by the Horners Company of London, which used natural plastics such as horn and tortoise shell to make various objects. In the 20th century, scientists create numerous synthetic polymers, such as bakelite. Nylon is created at DuPont in 1935. Formica, high-pressure laminate, is developed in the 1940s. In the 50s, architects like Eero Saarinen began designing furniture using fiberglass. By 1976, plastic becomes the most widely used material in the world. Plastic car bodies are introduced in the 90s. In 2009, Boeing introduces the 787 having a 100% composite skin. Today, the state-of-the-art in plastics includes nanomaterials and exotic fibers such as Kevlar for bulletproof vests, carbon fiber composites for aircraft, and such things as 3D printed body parts and plastic blood. Plastic is a unique material that presents far greater design opportunities than any other material. Composites. A composite is a mixture of two or more materials with properties superior to the materials from which it is made. Wood and bone are examples of natural composites. Wood consists of cellulose fibers embedded in a compound called lignin. The cellulose fibers give wood its ability to bend without breaking, while the lignin makes wood stiff. Bone is a combination of a soft form of protein known as collagen and a strong but brittle mineral called apatite. The earliest man-made composite materials were straw and mud combined to form bricks for building construction. Some other examples are concrete, which is a composite of cement, sand, and gravel, steel-reinforced concrete, steel-belted tires, and plywood with alternating directions of fibers. The reinforcing material of composites may be in the form of fibers, particles, or sheet laminates. FRP composites. FRP consists of reinforcing fibers contained within a solid polymer matrix. typically polyester resin, which cures from a liquid to form the solid matrix. The fibers are typically glass, made from sand, or silicon dioxide, basalt, or high-strength fibers, such as Kevlar or carbon. In fact, any fiber, including plant-based fibers of sufficient tensile strength, can be used in composites. Later on, we will discuss some of these fibers. The advantages of FRP include the following. FRP is resistant to a wide range of chemicals and is salt and freshwater proof. FRP will not rust and is resistant to termites. FRP does not warp or rot and is resistant to attack by insects. FRP has a very high strength-to-weight ratio compared to metals, wood, and concrete. Pultruded, or PFRP shapes, generally weigh 75 to 80% less than similar steel shapes and 30% less than similar aluminum shapes, making them easier to transport. PFRP shapes can be field fabricated by carpenter trades with standard tools and easily lifted into place during installation. Molded FRP can be fabricated into complex shapes. FRP can be made fire resistant with certain resins and additives. FRP does not require painting or other treatment. In architectural and civil applications, thermoset FRPs are mostly used, although stronger and stronger reinforced thermoplastics are being developed. A stress-strain diagram of an FRP composite shows high strength and tension of the fiber component. The resin component is much weaker. The resultant value shows that the two components together provide strength to the composite. The properties of a composite are determined by the properties of the fiber, the properties of the resin, the ratio of fiber to resin, and the geometry of the fibers in the composite. All of the foregoing items can be manipulated to achieve optimum results. The strength, hardness, fire resistance, and the type of resin and reinforcement can all be determined by the designer. There are so many variations possible in the design of plastics that the materials website MatWeb lists over 78,000 plastics. 11,000 of them are nylons. All of these plastics have different properties. In fact, FRP composites are a true designer material that allows an engineer to specify the exact properties required for a given application. An architect usually will not directly specify a plastic, but when dealing with industry sources and fabricators, it is useful to know what are the constituents of plastics and FRPs. Fiber reinforcement. Unlike metals and ceramics, which are isotropic materials, FRP composites are anisotropic, having different physical properties depending on the orientation of the fibers in the composite. Fibers can be arranged in a loose, random orientation called mat, or arranged in a fabric, or in the form of tape. FRP boat building uses fibers sprayed along with resin into molds using machines called chopper guns. Chopper guns spray cut lengths of fiber along with resin in a random pattern into the mold. Fibers that are arranged in one direction only are unidirectional and exhibit strength only in that direction. Fibers are also woven like any other textile and are known as weave. Fabric weave typically orients the fibers to 0 and 90 degrees, or the X and Y directions. This is known as multi-axial weave. Often fabric will be placed in alternate layers offset by 45 degrees. This creates quasi-isotropic properties and a much stronger finished piece. Note that while FRP is built up in layers, there is less strength in the Z direction, which occasionally results in delamination failure. Inert fillers, such as calcium carbonate, are often added to molded FRP in order to provide bulk. Chemicals, such as alumina trihydrate, are added as a flame retardant. Lightweight core materials are also added to molded FRP construction in order to achieve depth and greater strength. This is done especially in the boat building industry, where foam, honeycomb cores, and balsa wood are used. Resins. FRP resins are typically polyester, vinyl ester, or polyurethane. CFRP composites use much stronger epoxy resin. Each of these resins exhibits variation in properties such as strength, fire resistance, and corrosion resistance. Molded FRP. The most common method of FRP fabrication is by casting it into molds. This is known as hand layup or contact molding. Millions of FRP items are manufactured by molding, from furniture up to large recreational watercraft. The possible shapes of cast FRP are virtually unlimited. First used widely in the 1950s for boat hulls, fiberglass has demonstrated its utility by the fact that so many older boats are still in service. FRP is also durable enough for the facade of a building. The Mondial building in London was one of the largest buildings ever constructed with exterior fiberglass cladding. This 45-meter-high building was built in 1974 and demolished in 2006. An engineering study of the FRP panels was undertaken by the University of Surrey. It was determined that after 32 years of service, quote, visual inspection of these panels did not reveal any structural damage, with minimal weathering to the gel coat surface. Molded FRP can be manufactured in almost any shape and presents the designer with the most flexible formulation of all composites. In the building industry, molded fiberglass is the material of choice for such items as domes, arches, columns, and cornices. Molded FRP can also be given almost any exterior finish color and almost unlimited textures. Pultruded FRP. For most basic structures, PFRP or pultrusions are used. These consist of FRP versions of common structural steel shapes, such as angles, channels, I-beams, wide flange shapes, and square and round tubes, etc. Other profiles unique to the pultrusion process are also available. Similar to extrusion, the pultrusion process consists of pulling bundles of fibers through a heated die in the shape of the finished piece. The resin-saturated fibers are highly compressed by being pulled through the die, which forms an extremely dense composite. The fibers are continuously drawn from spools called creels. The finished pultrusion continuously emerges from the die as a completely cured thermoset. Pultrusions are then cut into manageable lengths, typically 20 to 40 feet. Pultrusions are cut, drilled, machined, and shaped much like wood. PFRPs can be managed on-site by carpentry trades. Pultrusions can be connected to each other using conventional hardware or with high-strength adhesives. Pultrusions were first manufactured for industrial uses, such as in paper mills, chemical plants, and other corrosive environments. They were used there as substitutes for steel in the manufacture of stairs, scaffolding, and even entire structures. Filament winding is a process used to make FRP pipes. With automatic machinery, carbon fiber tape is wound around a cylindrical mandrel. This machine can make pieces up to 40 feet long. This process could have application in architecture. Round, high-strength carbon fiber columns could be made with this machine. These would have much smaller footprints than conventional columns. Physical properties of FRP. In general, FRP composites exhibit superior properties to conventional materials. This bar chart displays the relative strength of the 9 most common engineering materials. The weaker composites match the strongest woods, and composites as a whole are as strong as the strongest metals and alloys. Shown here are interactive charts which display these materials according to various sets of values. Comparisons among and within the material classes are shown interactively. Hovering over a given material class displays the material types within that class. For example, on the strength versus cost chart, the envelope of values for composites displays GFRP at the lower range in expense and CFRP 20 to 30 times more expensive, but also 8 to 10 times stronger than GFRP. Note that these value scales are logarithmic. These charts are available on the Daniel J. Haggerty AIA website. FRP and recycling. The environmental impact of plastics is controversial. While the use of plastics has many societal benefits, plastics do have some negative aspects. For example, the production of PVC requires the formulation of large quantities of chlorine, a corrosive and toxic halogen. PVC also requires the addition of plasticizers, which tend to leach out of PVC as it ages. A technical solution would be required to solve this problem, the development of newer and more benign substitutes for PVC. One of the great advantages of plastics is that they are durable, but this can be a disadvantage. Disposable items made from plastics can constitute an eyesore and are persistent in the environment, hence the increasing need for recycling as a response to this problem. The Great Pacific Garbage Patch is a series of floating aggregations of plastic debris within the Pacific Gyre. Unless a cleanup effort is undertaken, this plastic will decompose into microplastics, minuscule particles harmful to marine life. While a technical cleanup solution is feasible, a social solution is also necessary, calling for more responsible disposal and recycling of plastic debris. Public awareness campaigns must be undertaken to attract public attention to the problem. Educational displays should be created, like this fish sculpture on a Brazilian beach made from discarded soda bottles. Thermoplastics are readily recyclable, since they are melted easily. Numerous items ranging from railroad ties to outerwear are manufactured from recycled milk and soda bottles. Thermoset plastics resist recycling due to their tightly cross-linked structure. They cannot be melted, but the constituent resins and fibers can be separated by chemical or thermal means. However, none of these methods has yet proven economically feasible. Mechanical shredding and recycling is proving effective. The Swiss concrete company Holcim breaks down thermosets by grinding them into pieces. They then use the pieces both as fuel for the kilns in their cement factories and also as aggregate in certain of their concrete mixes. FRP and sustainability. The most important development in sustainability in plastics is the creation of bioplastics and biocomposites. Biocomposites are composite materials made from organic fibers and resins. This is not a new development. The Ford Motor Company made automobiles from industrial hemp and soybean extract in its early years, and in 1941, Henry Ford himself demonstrated the strength and impact resistance of one of these composite vehicles by slamming it with a sledgehammer. This new technology was forgotten, however, as American industry geared up for World War II using primarily steel, such that steel became the easiest and cheapest material of choice for industry after the war. But this technology is making a comeback. In East Germany, the body of the 1957 Trabant was made from phenol resin and cotton fibers. In 2011, Motive Industries in Canada unveiled the Kestrel, an electric 4-passenger car made with industrial hemp bioengineered to produce maximum fiber. Hemp is a member of the cannabis family, yet does not contain sufficient quantities of THC to be used as a drug. It is a truly renewable resource. In addition to hemp, there are numerous other fibers used to make composites, such as banana, coconut, bamboo, quinaf, cotton, soy, flax, and many others. Shown here is a box beam made from bamboo fiber composite and epoxy resin. Here is a pultruded deck beam made from the fibers of quinaf, widely grown in Southeast Asia. Essentially, any natural fiber can be used as a reinforcement in a composite material. Bio-based resins are also being developed and certified by the U.S. Department of Agriculture. These are made from sugar, soybeans, castor beans, cashew nut shell oil, and byproducts from the production of biodiesel. Ashland Performance Materials of Ohio has developed Envirez, a soy and corn-based resin. It is currently used by the John Deere Corporation in building their agricultural equipment. The Campion Boat Company of Canada also uses Envirez to build their pleasure boats. Most molded FRP composites contain lightweight core material. Some of these core materials are themselves made from recycled composites. The Armacell Corporation of Belgium has developed core materials made of PET from recycled soda bottles. When these natural fibers are combined with bio-based resins, the result is bioplastic composite made entirely from renewable materials. FRP composites in the built environment. Considering the advantages of FRP composite and its constant improvement, the use of FRP in the building industry is one of the most benign and cost-effective uses of plastic there is. For the building industry, fiberglass composites are an almost perfect material. They are lightweight, strong, and extremely durable. They can be formed into virtually any shape and given almost any appearance. Composites can weigh as little as 20% of the weight of stone or concrete cladding. This means a substantial reduction in the dead load of a building. Shown here is the Eye-Catcher building, constructed in 1999 by the Fiberline Corporation of Denmark, one of the world's leading manufacturers of PFRPs. The Eye-Catcher building was constructed for a trade fair and later disassembled and reconstructed at a new location. Reduced weight means smaller crane requirements and easier erection. A reduced dead load means a smaller foundation and less support structure. A building with reduced mass means less swaying force during a seismic event. Because it is lightweight and strong, FRP is widely used in the defense, aerospace, and automotive industries. The building industry does use composites for bathtubs, shower trays, shower stalls, hot tubs, swimming pools, and window frames and doors. However, it has lagged behind other industries by not adopting FRP for the major components of its basic product, namely structural frames and exterior cladding for entire buildings. There are valid reasons for this. The building industry has a cautious and conservative attitude toward new and unproven materials. While other industries are compelled to experiment with new materials, the building industry is not. It can choose from a wide variety of reliable and time-tested materials. The result is that the development of FRP composites occurred in other industries. In the aerospace industry, the imperatives of national defense require the use of the most exotic and high-performance composites available for fighter aircraft and missiles. A new generation of naval vessels is being developed that are built of large amounts of composites. Almost unlimited budgets have allowed the defense industry to develop special composites, such as CFRP, carbon fiber reinforced plastics. Shown here is a carbon fiber beam. The commercial aircraft industry is driven by financial pressures. Every pound of weight reduced yields an average $330 annual cost savings. Over 30 years, this is almost $10,000 per pound of weight reduced. Today's most advanced commercial aircraft, the Boeing 787, is built from more than 50% CFRP composite by weight. The automotive industry uses various thermoplastics and thermosets, including FRP composites. Government-mandated fuel economy standards and general competition within the industry have forced manufacturers to eliminate as much weight as possible from vehicles. Similar economic and legal pressures are now impacting the building industry, primarily the issues of environmental quality, energy savings, and sustainability. Architecture will benefit from the use of composites for the same reasons as other industries. FRP composites provide direct applicability to several categories for LEED certification. The most significant factor limiting the adoption of FRP in the building industry has been the lack of standard design and engineering codes. This has recently changed with new design standards and code approvals. Since 2009, the ICC allows the use of FRP composites for interior and exterior applications as reflected in the IBC Chapter 26, Plastic, and Subsection 12, Fiber Reinforced Polymer. The most stringent certifications for FRP deal with fire and smoke generation. FRP products achieve Class A rating when they are made from fire-resistant resins and additives. For exterior use of FRP over 4 stories, passage of the NFPA 285 multi-story building test is required. This test requires a full mock-up of a wall section be tested by an open flame exiting a first-floor window on the exterior of the mock-up. The mock-up must survive a 30-minute fire. This test is difficult and expensive, and to date, few composite wall systems have been approved. One product which has passed is called FireShield 285, manufactured by Chrysler Associates, a California-based fiberglass fabricator. While several pultruders offer their own design manual, one difficulty for specifiers has been the lack of a universally recognized design manual issued by an authoritative source. The American Society of Civil Engineers has developed a standard for load and resistance factor design of pultruded FRP structures. Full adoption of the standard is expected in late 2015. FRP in civil engineering. In civil engineering, composites are an ideal material in several sectors. Some of the largest single items made from FRP are wind turbine blades. According to some sources, there are 70,000 deficient highway bridges in the U.S. that require rehabilitation or replacement. This represents a huge market for composite materials. There are quite a few examples of composite bridge construction throughout the world. These range from replacement of bridge decks to the construction of new bridges entirely from composites. Several companies have developed modular pultrusions that can be joined to create bridge deck structures. Entire bridges have also been replaced with complete FRP structures, especially in Europe. These bridges are fabricated from FRP components and often joined together off-site and delivered to the site in a completed state. Some bridges are fabricated in one piece the same way as boats by layup molding and then delivered in one piece to the job site. The extreme lightweight properties of FRP allow these large structures to be easily delivered and placed. The Pontresina Bridge is unique. It is the first composite bridge in Switzerland and was built using pultrusions. The structural members were connected using both adhesives and bolted connections. During the winter months, the bridge allows skiers and hikers to cross a frozen river. When spring arrives, the bridge is easily removed to prevent damage to it by spring floodwaters. FRP pipes play an important role in water treatment plants and in the infrastructure for distribution of drinking water. According to the World Corrosion Organization, the annual cost of corrosion worldwide is $2 trillion. Corrosion-resistant products are ideally suited to replace metal structures, piping, cooling towers, and much more. The versatility of composites presents an opportunity for aesthetic enhancement in this sector, as these cooling towers demonstrate. FRP in residential architecture. Architects have often stretched the boundaries of conventional design by attempting to incorporate fluid, curvilinear shapes into their work. In 1957, the Monsanto Corporation, MIT, and Disney co-sponsored the design and construction of a fiberglass house called the Home of the Future. This was displayed at Disneyland until 1967. Millions of people visited the house during its display. However, the public remained resistant to the idea of living in an enclosed plastic structure. That may be because designers were not aware of the aesthetic opportunities presented by plastics and composites. One seldom appreciated property of plastics is translucence. This house in Japan maximizes interior lighting by allowing daylighting to pass through the translucent walls. At night, the house returns to favor by bathing the streetscape with the soft glow of its interior lighting. While the public may not readily accept such cutting-edge home design, tasteful inclusion of curvilinear shapes and other FRP elements does have appeal. Few houses are designed entirely of FRP. However, there are systems builders and designers that fully utilize FRP for manufactured housing. NevHouse is a nonprofit group that uses recycled composite materials to manufacture prefabricated homes for affordable housing in less developed regions. The ease of transport and assembly and low maintenance of the homes take full advantage of the properties of composites. Other manufacturers have developed more conventional designs for prefabricated homes in the developed world. The Starlink system in Great Britain utilizes FRP composites to construct the entire home from the foundation to the walls and roof. Starlink is described by its developers as a modular construction system based on 10 pultruded profiles that link together using bolts and snap-fit construction to build houses rapidly. In the U.S., one company sells the Epitome Composite Foundation System based on prefabricated composite wall panels. FRP in commercial architecture. FRP is most fully taken advantage of in commercial architecture, such as this hotel in Singapore and this hospital in Qatar. The Milan Sheraton Hotel exclusively used PFRP to fabricate its very large exterior facade. The facade was constructed of curved, pultruded PFRP channels, onto which a pultruded PFRP skin was attached, in lengths of up to 66 feet. One large and innovative project was the thematic pavilion for Expo 2012 in South Korea, designed by Soma Architects. This building took advantage of the elasticity of FRP by creating a kinetic facade composed of louvers that open and close by actually twisting in order to create openings in the facade. In the U.S., one of the largest and most prestigious FRP projects is the exterior facade of the Museum of Modern Art in San Francisco, fabricated by Chrysler Associates. Chrysler is fabricating over 1,000 panels for this project out of its Fire Shield 285 system, with sizes up to 3 feet by 30 feet. A unique aspect of the MoMA project is that each panel is different. This is because Chrysler uses inexpensive disposable molds sculpted by a CNC machine from foam blocks, rather than permanent wooden molds that would have been far too expensive for the MoMA project. What is perhaps the world's largest FRP construction project is currently underway in Saudi Arabia. The Haramain Railway Station project consists of 5 stations for a 279-mile high-speed railway system. Designed by Foster & Partners, the project consists of structural steel columns supporting an FRP roof system fabricated from large composite panels. These are sandwich panels composed of a fire-retardant foam core enclosed within an FRP shell. The panels are triangular in shape and are assembled on-site into square sections 88 feet on a side. The panels have diamond-shaped windows to provide skylighting below. The total roof area of the 4 stations is over 1.7 million square feet. Large projects like these take full physical and economic advantage of composites and represent an important opportunity for the building industry. As architects begin implementing these new materials and techniques, 2 new technologies will have direct application. One is additive manufacturing, also known as 3D printing, and available from such companies as Stratasys and 3D Systems. This technology enables the creation of objects that conform directly to digital models created in CAD. A recent development in this field is the creation by the Markforged company of the first ever 3D printer able to manufacture objects in carbon fiber. Shown here are small architectural models printed in 3D. Additive manufacturing will soon scale up to full-size production capability. The opposite function is subtractive manufacturing, such as CNC machining. In composite fabrication, the most useful technology is water jet cutting. This allows the cutting of composites and any other material by means of numerically controlled nozzles, which use high-pressure streams of water to create extremely precise cuts up to several inches deep. In the northeastern U.S., there are water jet companies such as Advanced Cutting Services in Roselle, New Jersey. FRP composites will play an increasing role in architecture and present tremendous opportunities for architects. But this will only happen if progressive and forward-thinking professionals take the time to understand composites and begin incorporating them into their projects. For architects who wish to know more, there are several information sources dealing with developments in the composites industry. These constitute trade associations, industry cooperatives, magazines, and other publications. Information about these can be accessed on the Daniel J. Haggerty AIA website. Thank you for watching.